Hello everyone, my name's Sam Jones. I'm an R&D engineer at PowerFilm Solar. We manufacture custom thin film amorphous solar panels. And part of our product line is optimized for indoor use, which really fits into the IoT space, where you can implement energy harvesting to power low power electronic devices. So that's what I'm going to be talking about today, is creating self-sustaining IoT devices, and how energy harvesting kind of plays into that. As a quick overview, first I'll give a quick introduction into energy harvesting. I'll talk about the different energy harvesting methods. I'll dive a little bit deeper into ambient light collection, which is a little bit more of my expertise area. I'll talk about the hardware that you need to integrate energy harvesting into your electronic devices. So what is energy harvesting? Well, to understand energy harvesting, we need to understand what energy we're actually harvesting. And then in that, you need to understand what ambient energy is. So when we talk about energy harvesting, we're talking about harvesting ambient energy, or energy that is around us in our environment. And that can be anything from motion, heat energy, electromagnetic radiation in the form of lights, or even radio frequency waves. And most of these energy harvesters, they take advantage of some sort of physical phenomena that that's able to produce some sort of electronic current or potential voltage. Convert that ambient energy into electrical energy. And basically, modern technology has enabled energy harvesters to be more efficient and simpler, and actually make an effective solution as power sources for small, low-power electronic devices. And in the figure, you can see a couple different energy harvesting methods, and this is the composition of the market in 2014, and you can kind of see some of the different popular harvesting methods and how those are composed. So now that we know what energy harvesting is, you might be asking yourself, well, why is it important, and what role does that play in the IoT industry? Well, if you look at the figure I have here, the number of connected devices in the year 2025 is projected to be 25 billion. Every electronic device needs a power source, and generally that comes from a battery or a wall outlet. And batteries are cheap. But servicing and maintaining those batteries is expensive. And the biggest problem is that batteries are going to run out of power. They have a limited lifetime. So as soon as that battery runs out of juice, and you have to go and replace that battery or service and replace the entire module, that solution becomes obsolete and uneconomical. And that's where energy harvesting can pick up the tab and extend device lifetime and enable long lifetime devices. So if you look at the commercial IoT industry, an automated building could have upwards of 1,000 sensor nodes, and every time that a battery dies, that represents a huge cost for that building, to have to go in there and replace those parts. So energy harvesting could enable commercial building automation. So a couple examples of where batteries could actually represent a larger cost, and where energy harvesting makes sense and would be a feasible solution, would be home or building automation, where an automated building could have upwards of 1,000 nodes, and every time those sensors or devices, the batteries die, they need to be serviced and maintained. energy harvesting could be used to bypass that service and maintenance charge and actually enable the IoT solutions to be more practical and economical. And this is energy harvesting could play a role in the consumer market as well, where convenience is at a premium. In wearable devices, if you're asking the user to take the device off even once a week or once a month to charge the batteries, that every time they take that off, that's an opportunity for them to stop wearing them. Studies show that half the people that buy wearable devices stop using them within a month, and a major reason for that is because of battery charging. So energy harvesters could enable wearables to become less inconvenient, and that just means more data is going to be collected, and the IoT solutions are going to become more effective. And it's not only convenience and cost, but it could also represent a safety hazard. The National Fire Protection Agency says that 20% of U.S. homes have smoke alarms where there are dead or missing batteries. So that's one example of where dead batteries or the limited lifetime of batteries actually represents a safety hazard. And energy harvesting is not only going to take away the maintenance and service and enable long lifetime devices, but you also need to consider the environmental factors. 75 billion connected devices, that's a lot of batteries, and you have to consider the environmental impact of that those batteries have. Lots of batteries contain hazardous waste and heavy metals, and they take large amounts of energy to reclaim. So making the devices of the future, you need to consider the environmental factors. Energy harvesting can enable long lifetime devices and many times use non-toxic and environmentally friendly materials. So now that we know why energy harvesting is important and what role that can play in the IoT industry, let's kind of get power into context and how much power do I actually need and how much power can I get from energy harvesters. So I like to break down the power consumption into what sensors is your electronic device, or what sensors or functionality are you trying to do. If you're using a wireless protocol, that there's going to be power consumption associated with that. And then you can see the power generated from energy harvesters. So this diagram kind of puts that all together so that you can see the power consumption versus generation for different configurations. So when you're looking at sensors, a big thing is the sensor have any moving parts? A sensor that has no moving parts, such as temperature, pressure, humidity, or optical or motion sensors, those are going to be super low power, less than 10 microwatts. When you start getting into sensors that have moving parts such as gyroscopes and accelerometers, they're going to generally be a little bit higher power consumption, in the 1 milliwatt range. When you're looking at wireless protocols, the big driver of power consumption is the data rate. So low data rate, wireless protocols are going to have really low power consumption. So like if you're looking at Bluetooth or Zigbee or LoRaWAN, if your data rate is above every 10 seconds, then your net power consumption can be under 10 microwatts. But when you get into the higher data rates, such as 1 second or even as low as a couple milliseconds, your power consumption jumps way up, orders of magnitude. So then when you're looking at your energy harvester, you want to choose an energy harvester that's going to generate enough power for your application. So some sources of energy or harvesters such as electrodynamic switches and wearables and even ambient RF energy, they produce pretty low power, but they're still attractive options for certain really low power applications, and they can make some pretty cool solutions. Some of the larger power sources are thermoelectric generators, and solar can be optimized to generate larger amounts of power, and can be optimized for that. So now that we have put power into context, we have an idea of the power consumption versus generation for energy harvesters and applications. Let's look at each individual. Let's compare the different energy harvesting methods. So just quick overview, thermoelectric generators convert heat energy into electrical energy. Piezoelectric generators and electrodynamic generators, they convert motion energy into electrical energy. Radio frequency harvesters, they harvest radio frequency waves. Photovoltaic or solar harvests light. And to highlight a couple things from this table, just comparing some of the different parameters of the energy harvesting methods. A common theme of energy harvesters is the variability of the energy source itself. So if you look at solar, the sun, if you're trying to harvest energy from the sun doesn't shine all the time. It goes up and down every day, but that's also a very predictable process. So this idea of variability and predictability play hand in hand. You can design your system to take into account the variability of your energy harvester, because you can predict how it's going to react. And sometimes it's not always very predictable. If you're making if you're using a piezoelectric energy harvester on a wearable device, you might not be able to predict exactly how often that device is going to be used. So that all needs to be considered when developing and implementing an energy harvesting method. This idea of variability and predictability. So one major parameter that you need to consider when looking at different energy harvesting methods is the lifetime of the method. So if we're trying to replace batteries and the economic benefit of the energy harvester increases over time, we need to look at how long are these energy harvesters actually going to last. So I mean, if you look at thermoelectric and piezoelectric harvesters, they're subject to temperature differentials, and piezoelectric harvesters generally have moving parts. So those are kind of two possible breakdown methods that need to be taken into account through engineering to counteract. Radio frequency harvesters and solar panels have no inherent breakdown mechanisms. So they generally have very high lifetimes, over 20 years. And then another big thing is the cost. So generally, piezoelectric and thermoelectric energy harvesters are going to be a little bit more expensive as initial investment, whereas radio frequency and solar are going to be a little bit lower. And then you can compare that to a battery, which would be the lowest initial investment. But if you look at the economics over time, oftentimes you'll find that energy harvesting is a more economic solution. So let's dive a little bit deeper into the individual energy harvesting methods. So thermoelectric energy harvesting is the conversion of heat energy into electric power. So basically the idea here is one side of the thermoelectric material will be subject to a heat source, and then the other side will be cooled, or colder, and charges within the material, the way it's configured, will diffuse from the hot side to the cold side, and those diffusing charges will create a current that we can collect and use as power. And that power is heavily dependent on the difference in temperature between the hot and the cold side. The power will be maintained constant as long as that temperature difference is held. And usually that's held there using heat sinking. And that can either be to some cold source or out into the ambient air, just so that the cold side stays at a colder temperature than the hot side. And then again, this idea of thermal cycling will represent a mechanism for degradation, but that can be mitigated through engineering techniques. So maybe if you are generating more power than you need, you could insulate your thermoelectric generator to protect it from the higher thermal cycling. Some suitable applications are industrial equipment. Oftentimes manufacturing and industrial equipment generate heat, and that heat can be harvested and used to run monitoring equipment. There's a lot of IoT solutions for equipment monitoring and used for preventative maintenance. And those devices are often really low power and can be easily powered through energy harvesting techniques. Another big application would be wearable devices. The temperature differential on your skin is about, from your skin to the air, is typically around 10 degrees Celsius. And you can see in the figure, this plots power generation versus temperature difference. And at 10 degrees Celsius, you can generate close to 6 microwatts per centimeter squared. And a general rule is if an energy harvester can generate more than 1 microwatt of power, it can be used to power a really low power electronic device. So there are some cool wearable applications where thermoelectric energy harvesting can be used as a power source. Another application is actually residential power. So there's a company that makes really large thermoelectric generators, and they're meant to be placed near like a wood-burning stove or such, and that can actually supplement the power that's going to your house. So piezoelectric and electrodynamic harvesters, they convert motion or kinetic energy into electric power. And they take advantage of the piezoelectric effect or magnetic induction. So the way that piezoelectric material works is that when it is a force is applied to it, the way that the material is aligned, charges are squeezed out of it. And those charges can be collected. And then if the material is allowed to relax, it'll recover, and then when force is applied again, more charges will be produced, and those can be collected. So this kind of plays into the oscillation, apply force, relieve force, and that kind of goes into like an oscillatory system. So on the right, you see what is called a cantilever beam, and this is a popular configuration for piezoelectric energy harvesting, where you have a lever that is fixed on one side and a tip mass is placed on the other side. So when the entire system is moved, the tip mass, the momentum of the tip mass will cause the beam to oscillate up and down, and the piezoelectric material will be constantly squeezed and relaxed, and power can be constantly collected from it. So this idea of an oscillating system, the power that is generated is dependent on what's called the resonant frequency of the system. So the cantilever beam system is going to have a resonant frequency. And the way I like to think about a resonant frequency is if you are pushing a kid on a swing. If you try to push with a lot of really quick little pushes, or even large, very fast pushes, the swing is not going to move very much. You have to push the swing at the speed that the swing wants to go in order to make the swing move. And the same is true in the reverse when you're trying to collect energy from a system. So if you have say you have a piece of equipment that is vibrating at a certain frequency, you need to use a piezoelectric system or a cantilever beam that has a resonant frequency that is similar to the system that you're trying to harvest energy from in order to maximize the power collected. In that graph on the bottom right, you can see how much the power drops off, even if you get 5 or 10% away from that resonant frequency. The power generated is orders of magnitude smaller. So if we look at some applications where piezoelectric or electrodynamic harvesting makes sense, you can look at industrial equipment or vehicles. Oftentimes they are vibrating or moving, and that movement can produce enough power to power some of those monitoring equipment or other IoT devices that are monitoring that equipment. Another interesting application area is wearable devices, where power from biological movement is harvested. One major obstacle for wearable devices is that biological movement is generally lower frequency and lower amplitude. So cantilever beams currently have a resonant frequency from anywhere from 100 to greater than 1,000 hertz, whereas biological movement is in less than 10 hertz range. So currently a hot research topic is trying to make piezoelectric configurations with low resonant frequency so that you can match the biological movement and actually collect enough power to run those electronic devices. And another big thing about piezoelectric harvesters is they can be scaled to the microscale level, and they can actually be fabricated on chips and create a power source for your system on a chip, microchip devices. So that's a big area in MEMS. And then getting back to the electrodynamic, mechanical switches are actually a really good application for electrodynamic devices, where you have a magnet that is pushed through a bunch of coils of wire, and that the current that is produced from that is used to send out a beacon pulse or do a different functionality. So radio frequency harvesting is the conversion of radio waves or RF activity into electrical energy. And you can break it down I like to break it down into two major categories, near field and far field. So far field RF is your typical personal area networks like Wi-Fi or Bluetooth or Zigbee, and your like TV broadcasts and cellular signals. Those are all far field communication. They use antennas to collect and receive and transmit signals. Near field, they actually use magnetic coupling. And the way I like to think about magnetic coupling is if you hold two magnets really close together, they kind of couple together. And if you try to turn one, the other one is going to also want to turn. And you can use that for communicating, sending bits, ones and zeros, or you can also use that as a power source and collect that power to then resend a message. And that's actually a pretty mature technology that's used in credit cards and access tags. So cellular and TV broadcasts are example of far field radio frequencies, and those can be harvested by using a rectifying antenna. So basically it's similar to the antenna that you would use to transmit and receive, but it's just configured to actually collect and store the power that it receives rather than using it for communication. And basically the power that is collected is dependent on the amplitude or the power density of the signal. So if you're trying to harvest cellular or TV broadcasts, you want to be in an area that has high traffic. And you can see in the bottom right table some of the different cellular bands and how much power density there are. So in some of the bands, you can get close to 10 microwatts per centimeter squared of power available. So that would be more than enough to power some low power wireless electronics. Another way that you can harvest energy is by rewriting protocols in order to fill silent periods. So a large problem in harvesting, say, Wi-Fi is that there will be periods where there's high traffic, and then there'll be large periods where there's no traffic. So in order to make that a viable power source, there needs to be something to fill those silent periods. So a group put out an article defining what is called power over Wi-Fi, where they rewrote the Wi-Fi protocol to fill those silent periods with basically random noise. But that random noise can be harvested at the end devices and used as power. So basically, suitable applications for RF harvesting is anywhere where there's heavy RF traffic. So within a city typically has good cellular and TV coverage, so that you would be able to harvest a lot more power versus if you were out in the country or in a rural setting. Also, inside buildings and homes often have Wi-Fi or Bluetooth, and those protocols could be reconfigured to provide power. So applications are home and building automation, smart cities, those types of devices that work in those networks could be reconfigured to run on RF power. And then, like I said, near-field communication, RFID, is somewhat of a mature technology today that runs completely off of RF power. So photovoltaic energy harvesters absorb light and then convert that to electrical power. And basically the way that works is the semiconductor material inside the solar cell separates the charges that are produced when light is absorbed, and that's how you get your current and your voltage. So power generated from a photovoltaic energy harvester is heavily dependent on the intensity of the light source. So when you're talking about intensity, it's good to think about outdoor versus indoor, and I'll get into that a little bit later. But solar can be optimized to collect indoor light or outdoor light. And although the photovoltaic technology has been around for quite a while, using solar in an energy harvesting setting is a relatively new and emerging industry. So one major advantage of photovoltaics is that they're simple and they're easy to integrate into electronics. Much like a battery. A battery will provide a constant DC voltage and variable current, whatever the electronic system needs. And that's kind of a solar panel will provide a DC voltage and DC current to match, and you can configure and customize a solar panel to match the voltage and current levels of your system. So in that sense, it can be very easy to integrate into your electronic devices. In some cases, only requiring a couple components to do so. And for that reason, photovoltaic energy harvesting, when compared to the other energy harvesting, has a lot of application advantages. There is light available in many places. Indoors and outdoors, people need light to see, so that light can often be harvested and used as a power source. So obviously, home and building automation typically use really low power sensors, actuators, and those can be run off of solar light, solar energy harvesting. Sensing applications indoors and outdoors, asset tracking indoors and outdoors, and even wearable devices. PowerFilm makes thin film amorphous solar panels, and they're lightweight and durable and flexible. They can actually be sewn into fabric and clothing, so that can be used in a wearable application. So now that we have an idea of photovoltaic energy harvesting, let's look at the different solar technologies and kind of compare them side by side to get a better idea of what's available and what's the right choice for you. So when thinking about the different solar technologies, a good way to think about it is thin film versus crystalline. Crystalline solar technology is the mainstream. If you see a solar panel on a roof or driving down the road and see it on a construction sign, that's generally going to be a polycrystalline or monocrystalline solar panel. They are thicker. They are generally higher efficiency. They can be higher efficiency at a lower cost, and that is why they are so popular. But because they are thicker and a crystalline diamond structure, they're more prone to cracking, and they require that bulky aluminum frame protection and glass top. And for that reason, they're obviously not flexible. So thin film, such as amorphous silicon or gallium arsenide, is going to be ultra thin and flexible, inherently durable. Amorphous silicon suffers from lower efficiency, so a larger area is required to get the same power output as a crystalline or gallium arsenide solution at a moderate cost. So crystalline solutions can be a lot lower cost since they're mass produced. Gallium arsenide is going to be a extremely highly efficient, but at a very high cost. A lot of times people will say, can I use a solar panel indoors? And that's kind of a complicated question, which I'll try to answer here. And to do that, we need to look at, well, what is the actual difference between indoor and outdoor light? So outdoor light is going to be a continuous spectrum. So when I say spectrum, I mean you can think about it as the color of light, quite literally. The sun has a continuous mixture of all the different colors of light throughout the entire spectrum to get the white color that we see. When we move indoors, we're using artificial light bulbs, and those light bulbs are not going to be a continuous mixture of all the colors. They're going to be a mixture of a couple different specific colors that combine together to get the light that we see. So some examples are fluorescence or LEDs, and those are discrete spectrums. So a fluorescent spectrum are going to have a number of really distinct sharp spectral peaks, and that's going to be what the spectrum looks like for those. LEDs have like a couple broader peaks, but still more discrete than what would be an outdoor full spectrum. So when you think about how that relates to solar and how that affects us, the way that a solar panel works, you have to look at what's called the quantum efficiency. So what the quantum efficiency does is for a solar panel or a solar technology, it'll go through each color and say, this is how well I can collect light from this specific color. So on the bottom right, you can see the quantum efficiencies of a couple different solar technologies. And what you want to do is match the spectrum of the light source to the solar technology. So amorphous silicon, if you can see, the quantum efficiency goes down at about 650 to 700 nanometers, or the reddish light. So anything below red light, amorphous silicon absorbs well, and that's called the visible spectrum. So amorphous silicon is well matched to absorb light in the visible spectrum. Other technologies such as crystalline silicon, gallium arsenide, those are matched to the outdoor spectrum, and they absorb light in the near infrared light sources that are outside of the visible spectrum. And sometimes when you take solar that's optimized to absorb light in that infrared spectrum, and you take it inside where that infrared spectrum is non-existent, the solar panel may not work properly and may not work at all. So when you are designing a system, a solar harvesting system, you need to consider the spectrum of the light that you're absorbing and match that to a solar technology. It has a quantum efficiency that absorbed light in that spectrum well. So now that we understand the spectral differences between indoor and outdoor light, let's look at kind of the power density and how much power we can generate at different light levels. So to do this, we're gonna look at what's called lux. And lux is a measure of intensity as perceived by the human eye. So a light bulb is going to be rated to generate a specific number of lux or light rays, and that can be correlated to the power that's generated from the solar panel. In the bottom left corner, you can kind of see that's how lux is defined. Each color is kind of given a weight, and that's how our eye perceives light intensity. So if we look at the charts on the right, the top one is a larger range from direct sunlight all the way down to the indoor spectrum, and those are on a log scale, since the intensity of light outside can be up to 100 times more intense than indoor light. Under direct sunlight, you can get around 1 milliwatt per centimeter squared. So if we look at the outdoor light levels, under direct sunlight, which is about 100,000 lux, we can collect around 4 milliwatts per centimeter squared using amorphous silicon technology. If you move down into a shaded area, you're going to be around 10 to 25,000 lux, and at that level, we can collect 400 microwatts. Moving to the indoors, so an indoor area that's next to a window or a room with a window, you're generally going to see anywhere from 500 to 1,000 lux. And at that level, you can produce around 32 microwatts per centimeter squared. If you move into a room without a window in it, you're going to be around 300 to 400 lux. And at that level, amorphous silicon produces around 13 microwatts per centimeter squared. On the lower end, light level in like a warehouse is going to be around 200 lux, and you can generate about 6 microwatts per centimeter squared. And if you remember back to my rule of thumb, if you can generate at least 1 microwatt, that's enough power that can be harvested to power low power electronics. So now that we know how much power we can produce, what does that actually look like? So a solar panel, the generated power is characterized by what's called an IV curve. And if you think about power electronically, it's equal to the current times the voltage. So a solar panel, when it absorbs light, charges are created, and the solar panel separates those charges, and a voltage will build up if those charges don't have anywhere to go. And that's what's called the open circuit voltage. Once you short that panel together, those charges will flow, and a current will be formed, and that's what's called the short circuit current. And since current or power is equal to current times voltage, at those two levels, one of them is going to be zero, so your power is always going to be zero. So what you want to do is be somewhere in between, where the current and the voltage are maximized to produce the maximum amount of power. And that's called the maximum power point. So the voltage and the current that are produced by the solar panel are dependent on two things. The voltage is dependent on how many cells are connected in series in the solar panel. You can see the bottom left figure shows what a series connection solar panel looks like. And each cell of a solar panel is going to add a specific amount of voltage. For amorphous silicon, that's either 0.6 volts for single junction material or 1.2 volts for tandem junction material. So you can kind of put together the number of cells that you need to match the voltage of your application. And to match the power, you just scale the current. And that's done by increasing the overall area of your solar panel. And that's represented on the figure on the right. The curve is shifted up when two solar panels are parallel together. So you can kind of use these ideas to create a custom solar panel with a custom number of cells and at a custom area to get the voltage and the current and the power that your electronic needs. So one unique advantage of roll-to-roll processing of amorphous silicon is the ability to implement custom laser scribing and screen printing processes. So solar cells can be cut to a specific number of cells. Total area can be customized, shape can be customized, and then custom screens can be printed to connect all the cells together. And this lends itself to rapid prototyping, rapid custom solutions, solar solutions. So now that we know what the power looks like, how do we actually use that power? How do we put it into a battery or convert it to the voltage, the specific voltage that we need? And that's done a couple different ways. One way is through power management IC or PMIC. And this implements a DC to DC converter, either a buck converter or a boost converter or sometimes a charge pump, to convert the voltage of the panel to the appropriate voltage of your system. So a solar panel, the voltage will go up and down based on however much power is being drawn from the system. So if your system needs a constant and stable supply voltage, a DC-DC converter can convert the DC voltage of the panel down to or up to the stable supply voltage that your electronics need. And another big thing, a big feature of power management IC is the ability to implement some sort of max power point tracking. So if you think back to the IV curve, there was that sweet spot on the IV curve where the power that is collected from the solar panel was maximized. So max power point tracking can be used to make sure that the panel is operating at that max power point. That can either be a set voltage or a ratio max power point tracking where the controller will always set the max power point to a certain percentage of the open circuit voltage. Or it can be true max power point tracking where the power management IC actively records and tracks and will adjust the max power point on the fly to get a true maximum power point tracking. Another good feature of power management IC is the ability to implement battery charging schemes and battery protection. So common battery chemistry such as lithium ion or lead acid, they need to follow strict battery charging schemes, and if those are not followed, then the battery can be damaged. And by itself, a solar panel, it will overcharge and damage a battery if left directly connected. So power management can disconnect the solar and make sure that the battery is being charged properly and it is protected. The major drawback of a power management IC is increased components, cost, and board size. So you can see in the bottom left figure, that's an example of a schematic of a power management IC, versus on the right, you can see a direct configuration where there's only two components required. So you are sacrificing cost and footprint for the increased features and performance. So if you're looking for the lowest cost and the smallest solution, in some specific applications, a direct connection or a direct power or direct charging solution can actually be implemented. So on the bottom right, you have a solar panel that's connected to the output through a diode, and it charges a capacitor as the storage element. And basically the thing you have to consider when using this is the rating of the components of your system. So oftentimes microprocessor ICs, they can run off of anything from 1.8 volts up to 3.6 volts. So if you can size your solar panel to operate within those parameters, a direct power solution could be the right choice. Obviously, you're not going to have the features that the power management IC has. There's not going to be any stable DC-DC conversion or maximum power point tracking, and you can't charge a battery or implement any sort of protection. But this would be sort of like a bare bones, super cost-effective solution that could be viable in certain applications. So now that we have learned a little bit more about energy harvesting, let's see what a real-life example would look like. So this demo runs off of indoor solar, powers a Bluetooth low-energy sensor. So the energy harvesting unit consists of amorphous silicon 2.4 volt low-light solar panel, and then uses a power management IC, the BQ25570, with ratio max power point tracking, and it uses a 1800 microfarad capacitor as a storage element. The wireless sensing unit uses TI CC2650 wireless MCU, and it's running the power optimized Bluetooth low energy stack. And the data and the sensors can be configured and monitored using a connected Android data monitor application. So overall, we've seen what role energy harvesting can play in the IoT industry in making completely self-sustaining IoT devices a reality, and how the importance that will play moving forward into the future. We've seen the different types of energy harvesters and which applications make sense for them. And specifically, we've seen how versatile solar energy harvesting can be, and the number of the wide applications where solar harvesting actually makes practical and feasible economic sense. I'd like to thank you all for listening today, and feel free to contact PowerFilm with any questions or inquiries.